Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is Introduction to Solid Modeling in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. I always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. As far as the content over the next hour today, I want to give a brief overview of the various solid types and definitions available within our FEA program, RFEM. We'll also go over the material model considerations, including linear and nonlinear. And then we'll move into the relevant examples. And with these examples, we'll go ahead and discuss the modeling workflow, including some nonlinear applications there as well. We'll run an analysis, and finally, we'll go over the results. So there are 4 different types of solids within RFEM, and the first is a material solid. So this is a 3D object, meaning that we have a finite element mesh in all 3 directions. The material can either be isotropic or orthotropic. So these material solids are defined by null boundary surfaces, and null just meaning that we're not contributing to any of the stiffness within the calculation. We're purely using these surfaces just to define the geometry for the 3D solid. The second type is a gas solid, where we would define ideal gas properties. We'd also define an initial pressure and temperature condition, and we might be wondering, what could we use gas solids for? Well, we'll see an example later on today where we use this for an inflated foil cushion. It could be used for a gas tank. We also have our additional add-on module within RFEM, RF Glass, which does a general stress analysis and design, including for insulated glass panels. So essentially what's happening underneath the hood is the program is going to create a 3D model, which also includes a gas solid sandwiched in between the glass layers. We also have a contact solid. So this solid is actually used to model the contact properties between 2 surfaces. So over on the right-hand side here, you can see we have surface A and surface B. We would actually give those surfaces a material and a thickness, unlike the null surfaces for material solids. And we're using this contact solid to define nonlinear contact conditions between those 2 elements. For example, failure under tension or rigid friction. Now, contact solids do have strict modeling requirements, so we'll go over those a little bit later on in the presentation. And the final solid type is a null solid. And essentially, when we set a solid to null, which we can see over here on the right-hand side with this picture, this red solid is set to null, well, then the solid itself and any associated loads are not considered in the calculation. So we might want to use this option to quickly make changes within our model and to run the calculation considering the solid, but then we can reactivate it without having to redraw it again. So there are several different material models available for solid elements within RFEM, and I want to preface that the linear elastic materials by default are included within this main program. If you want to take advantage of any of the nonlinear materials, then this would require the add-on module RF Mat NL. So it simply releases these nonlinear material models within RFEM. Now, the first one listed here is an isotropic linear elastic material, again, default within the program. And essentially, the linear elastic stiffness properties do not depend on the directions. And we can clearly see here there's a linear stress-strain relationship. The second type is an isotropic nonlinear elastic. Again, you would need RF Mat NL for this material model. And this same stress-strain relationship applies for both the unloading and the loading phase for the material. No permanent plastic distortion will occur, though. Then we also have the isotropic plastic material model. This is where elastic and plastic zones are defined, and the calculation will be carried out iteratively and with multiple load increments. So essentially with this model, if a yield stress is exceeded on a particular finite element mesh point, the modulus of elasticity is immediately reduced. The calculation is rerun until we have full load distribution on the entire structure. Then we also have orthotropic elastic. So this allows us to define elastic stiffnesses separately in all three directions. We might want to use this material model for something like wood or timber. Over on the right, we have orthotropic plastic. So this utilizes the Tsai-Wu failure theory, and it allows for both plastic and orthotropic properties to be defined in three directions. Finally, the last two here, we have an isotropic thermal elastic, and this is a temperature-dependent stress strain where properties can be defined. And you can see we can import in from Microsoft Excel, for example, to go ahead and generate this relationship. This is beneficial for thermal loads where the modulus of elasticity can be reduced for higher temperatures, for example. And then finally, we have isotropic damage, and this might be used for steel fiber reinforced concrete where a continuous reduction of strength will occur due to cracking. This utilizes Mazar's damage model, and an isotropic stiffness is reduced with a scalar damage parameter. All right, so now that we have covered the different solid types and material models, I would like to get started with our first example here within RFEM. So you'll notice that I have a series of line and node elements here, and this model actually comes to us from the firm GP Joule Canada out of Toronto, and they use this type of connection here for their solar racking products. And they have delivered me to this file as an IGES. So what I did under File Import, you can see here that we have many different file extensions that we can import directly into the model. We also have some direct interfaces with Tekla, Revit, AutoCAD. These are all default within the main program. If you are trying to import an STP file, a step file, IGES, you will need to utilize the add-on module RF link. So for today, we're importing in this IGES. We'll use that RF link, and essentially what will be brought in are a series of line and node elements to help us model these solid elements. So to begin with, we could probably agree that this is a little bit more of an odd connection, not really found standard in a lot of connection design. So this might flag us that we'd want to do finite element analysis with solid elements to view the various stresses and deformations within this model. So we'll begin by drawing our first solid here. And we can see from these vertical lines as well as the circular lines at the top and the bottom that we want to begin with drawing our first pipe solid. I'll go up here to draw a new surface element, and all of these surfaces from these drop down allow us to draw a surface that's in a single plane. So we'll choose the select boundary lines, and we're going to set the stiffness to null. So if you remember back to the PowerPoint, these null surfaces will define essentially the geometry of this, what will be eventually a solid element. I click OK. And then I can zoom in here to the top of what will be my pipe element, and I'm just going to select these various line elements here to create my first null surfaces. Now we'll do the exact same thing on the bottom. I'm just going to zoom in here and select all 4 line elements, and we'll do so on the other side as well. So as far as the pipe walls, these are not in a single plane. So we cannot use this option here to just draw a simple surface, but rather we need to use this tool a couple over for a new quadrangle. Now again, the stiffness type is set to null, but this allows us to define surfaces that aren't necessarily in a single plane. So you can see here that I'm going to define my outer wall, and then I'm going to define my inner wall with these 4 simple lines. Now I can take both of these surfaces here, select them, and utilize my mirror tool. We can create a copy with the mirror tool. We would mirror about the ZY plane, And then I can just simply select any point here within the model that I'd like to mirror about. The coordinates are automatically populated, and now we can see here that all of our null surfaces are now complete. So we can define our first solid. Up here in the toolbar, I choose the option New Solid. The solid type will be set to material. So here are those 4 different types that we discussed in the PowerPoint. The material will be accessed from the material database. So I'm going to utilize my filters on the left to choose metal. We'll choose steel. We'll choose the ASTM, and we can even take it a step further to choose the AISC 360. And from here, we would want to choose A53 grade B with the relevant material properties given to us. So I click OK, and then it's really just as easy as graphically selecting these boundary surfaces. So surfaces 1 through 8. Now the other 2 tabs here, the FE mesh allows us to define an FE mesh refinement. We'll actually do this a little bit later on. So we'll leave this as unchecked for now. The axes tab will allow us to modify the local axes of the solid. We'll just leave this as the standard default. So when I click OK, what we'll see here then is our first solid has been defined, and we can select it here, right here in the center of all of these null surfaces. So that was a fairly easy solid to define, but what we would like to move on to is maybe a little bit more complex of an example. So the second solid will be this plate that is essentially resting up against the face of this pipe element. I'm going to select all of my nodes and my lines, and we'll begin by generating those same null surfaces. So I go to my surface option here to select the boundary lines. The stiffness is still set to null. I click OK. And what this will allow me to do is just to move around the model here in a circular fashion, and we can rotate the model to generate our first null surface. Now, the exact same thing needs to be done for all of these smaller surfaces around the edge. So I'm just going to, again, move around in the circular direction. I'm going to skip this curved surface. And we know the reason why, because this is not in a single plane. So my element that I am utilizing right now only allows me to define these surfaces in a single plane. And we'll actually utilize these curved surfaces here on the side because these are in a single plane still, and we are done. So this top surface, I need to copy it down to my bottom. So I will highlight it, hold down my control key, and then I can actually just drag and drop and make a copy. And you can see I kind of am slightly off there. No worries, we'll hit the undo. Can zoom in here, drag and drop, and let's try and snap that to this point here again. So now we have that null surface shown on the bottom. Now for these curved surfaces, we need to go back to that quadrangle. So I'll choose the quadrangle option here within my toolbar, and then I can easily select the 4 lines to create that first curved surface. And we're also going to do the same thing where our plate here transitions from these horizontal elements to the vertical elements, and we need to do so on the back side as well. So those null surfaces are now complete. And rather than doing that exact same process on the lower half, what I can do is to select all of my elements here. I can once again utilize my mirror tool. We will mirror about the XY plane. We'll create a copy, and then I can graphically select my mirroring point. You'll notice the program will snap to one of the midpoints of these vertical lines. So when I click OK, then all of those null surfaces are shown at the bottom here as well. So moving on to the center portion of our steel plate. Well, we can utilize our surfaces in one plane once again, and this is easy enough to select this front face here of my plate element. But you'll also notice that we need to add in some openings. So before I do, let me just add in the side surfaces here. And to add these openings, we have the option right next to the surfaces to select the boundary lines for an opening as well. So then I can easily just select these circular lines, and the program automatically detects that it should add an opening directly within this surface. So once I have selected all 6 openings for my bolts, I'd like to copy this same surface and the openings to the other side. So I'll highlight this surface, but then I can also hold down my control key, and I know it's a little bit difficult for you guys to see, but I'm also selecting all of the openings. Well, here is where we can easily hold down our control key, drag and drop to make a copy on the back side as well. So now you'll notice those openings are also on the back of the plate. And realistically, we think we should be ready to create that second solid. So I'm going to go up here, just like the pipe, to create a new solid. The solid type will be set to material, but let's define a new material from our database. And this time we will utilize steel A36. I click OK. Now I choose my boundary surfaces, and what you'll notice when I click OK is the program automatically gives me a warning saying the surface boundary is not closed at these particular edges. So these are all specific lines. Well, the problem is that we define these openings, but we didn't close the surfaces here on the interior of the openings. So what this would require then is a new quadrangle surface. We click OK, and we actually need to apply these surfaces on the interior here. So once I apply these 2 surfaces, what you'll notice is I have these 2 additional surfaces. I can hold down my control key. We can drag and drop to these additional openings, and we can do so on the other side. And making sure that our snap points align. And finally, we have one more opening to add here. The other thing I'm going to do quickly is to utilize this tool up here in my toolbar. It's the connect lines or members. All that this does is recognize where lines are connecting, nodes are connecting, and we'll go ahead and create an intersecting node there. So let's try and create our solid again. Solid type material, I'm going to select the steel A36 that I've already defined, and let's select all of our null surfaces here, and I can click OK. And so now you can see that surface was generated just fine once we close those boundaries, and we have an additional solid shown here. So we can cancel this visibility here, and let's take a look at the display of our model according to the material. And I'm going to change the color of steel A53 here to a green color just so we can see the difference. Now, here's the problem if we were to continue on modeling the rest of our solids and eventually run an analysis. If this plate was to press onto this pipe in compression, the plate will actually just pass right through the pipe. The program doesn't detect that these 2 elements are connected. And the reason why is because they do not have a commonly shared surface. So what can we do about this? Well, I think we can agree on the commonly shared surface should be this curved surface here that we created that's a part of our plate. Well, the reason why the pipe currently does not detect it is just because we need to integrate that surface directly within the solid itself. So I'll begin by drawing a new opening by selecting the boundary lines. And let me turn this into a wireframe view, and I'm going to select the 4 lines here. And I now have an opening symbol shown. Now this surface still exists in the interior of this plate element. So we'll take this a step further then, and what we'd like to do is to double click, and actually let me back up a step. We'd like to double click on the null surface. Remember, this is part of the pipe here. It might be a little bit easier to see when we are in a rendered view. We'll change this back to a wireframe view. I'm going to double click on this null surface of the pipe, and under the integrated tab, I actually need to select this opening and tell the program, okay, integrate this opening directly within this pipe. So we've done that with opening number 13. Then I'm going to double click on my pipe solid here, and under the boundary surfaces, I want to select that commonly shared curved surface here between the plate and the pipe element. Surface number 19 is now listed. So I can click OK. So now we have integrated that surface, this curved surface here, between both the pipe element and the plate element. So now when they bear on each other, the program will recognize that they're actually connected. So we'd also want to do the same thing at the bottom here, and we'd want to continue on drawing all the rest of our solids. So for the sake of time, you'll notice here that I have continued on with the rest of the model, and I've added in that opening down here at the bottom and integrated that surface to the pipe as well. But we can also access a list of our solids under the Data tab within our Project Navigator. And you'll notice that I have additional solids now drawn for this U-shaped rod that's essentially tying this plate element around my pipe. We also have, of course, the pipe element. We have the plate that we just created. Then we have some additional solids, including a solid defined for our bolt on the left. We have maybe a bolt on the right. And then we have some additional solids for the bolts connecting our double channel here to this yellow plate. And eventually this yellow plate connects, back to this initial solid that we had just created. So you'll also see that we have solids defined for these channel sections. This is a double channel. It's representing our diagonal brace in this connection. So before we're ready to run an analysis, of course, we need to load the structure and we need to support it. So let's begin by supporting it with new line supports. I'm going to access a new line support, and we have a couple default options, both hinged and rigid. We can always create a new line support, and this allows us to define any of the 6 degrees of freedom here as fully fixed, fully released. Of course, we have partial fixity and nonlinear options. I'm just going to choose the default hinged option. I click OK, and we will just select the top and bottom of the plate element here. So now we have a line support at both the interior and the exterior of this pipe. So it's now supported. We'd like to move on to loading. And with the loading, we probably want to represent some type of load on this diagonal brace. And it's most likely easiest to just simply apply a nodal load. But the problem is that we have all of these surfaces here, these null surfaces. We'd like a point load to really distribute it evenly across this entire face. So how do we do that? Well, I'm going to select all of these surfaces down here at the end, and I'll create a visibility by the selected objects. Right now, all of these surfaces, if we were to highlight them, and we can right-click to edit the surface, we're actually going to change these from null to rigid stiffness. So a very, very high stiffness, so that eventually when we apply a single point load, then that will be distributed evenly across these entire faces. So I click OK here. But we need to take this a little bit further and actually connect these two faces here as well. So I'll draw an additional rigid surface element between these two channel sections. I'm going to use a new line element, and I'm going to zoom in here to select my point on the left and my point on the right. We're also going to do the same thing up here at the top. I'm going to select my point on the left and my point on the right. I'm going to utilize this connect lines or members tool once again, just so the program detects where these lines are intersecting these additional surfaces. And we once again draw a new surface by selecting the boundary lines, but this time the stiffness will be set to rigid instead of null. And I'm just going to move around here by selecting these various nodes that make up the boundaries of this rigid surface. So here we are, rigid surfaces connecting both of these channel sections. Now I'd like to create a node right here in the center. So I can go up to my toolbar, and instead of just drawing a new node, we have the ability to draw a node between 2 points. So I can select my point on the left, my point on the right, and automatically the program will place a center point here. So this is going to be the node that we want to use to load this entire connection. So before applying a nodal load, we want to generate some various load cases. So I use this option here to create a new load case. The first load case description is going to be up. And we're going to place a load that's completely in the vertical direction. Self-weight is activated here. I'm going to make a copy of this, and today I'm just going to be utilizing load cases rather than load combinations. So therefore I'll activate self-weight here because I'm not combining any of these loads, I'm actually running them separately. And we'll create one more copy and we'll call this one a tension load. And I click OK. So now that we have our load cases defined, I'm going to choose the up direction here. I'm going to apply a new nodal load. And within this dialog box, I'm going to select the magnitude and enter this in as 20 kips in the vertical global Z direction. I click OK, and then I can just simply zoom in here and select the single node. So now we can see our upward load shown here. Exact same process for down. I'm going to apply a new nodal load. The only thing that I want to modify here is instead of using a positive 20, we will apply a negative 20 kips. So just adding a negative sign in front of that, we select that center node, and now we have a downward load. So for this last load case, this tension load, and this is probably the most realistic load, we'd like to apply some type of tension load along the same orientation as this diagonal brace. So when we go to draw a new load, we might be thinking, okay, we must have to break down this diagonal load here into horizontal and vertical components. But we have a nice feature within the program that allows us to define it by direction. So I can go into the detail settings here, and I can actually define this load in the same orientation that a line is defined as by selecting it graphically within the model. So I can graphically choose any one of these arbitrary lines that are in the same direction as my member, line 324. I click OK. I set the magnitude here to be negative 40 kips. I click OK, and then I'm going to scroll in here, select that center node again, and now you'll notice that we have this diagonal load defined along the length of the diagonal brace. We didn't have to break it up into the horizontal and vertical components. Okay, so we are almost ready to run our calculation. The final thing to discuss is the FE mesh. And under Calculate FE Mesh settings, the default typically for a new model for a global mesh will be 1 foot. Instead, this is entirely too big for this type of smaller scale model. So we'd like to change this to 1 inch, and we can select this option here to regenerate the FE mesh when we click OK. So we can see down here in the lower left-hand corner, the program's kind of thinking through to generate this FE mesh at a 1 inch length. So once this is completed, the program will go ahead and exit out of this dialog box, and we can generate the, or we can turn on the FE mesh under our display tab here. Let's turn this to wireframe view, and you'll notice that the program has automatically generated this FE mesh, tying all of our nodes, our line elements together, the solids. We don't need to take care of anything manually. And let me take a look at one of these smaller bolt solids, for example, and I'll create a visibility by the selected objects. One thing that I'd like to know when we're kind of zooming in here is that there's actually only 2 FE mesh elements across the entire length. And if we're truly interested in the stresses in our bolt elements even, we probably want to refine this mesh quite a bit. So what I'll do here is to cancel my visibility mode, and holding down my control key, what I can do here is to select all of these smaller solid elements. And I'll set my visibility by the selected objects. We can right click to edit the solid, and we'll revisit this FE mesh tab where we can create an FE mesh refinement. So a refinement will allow me to define something smaller here than the 1 inch global setting, 0.3 inches for the entire solid. Now, in addition to these smaller elements, and you can see the FE mesh refinement shown here with this cube type symbol, if I take a look by canceling my visibility mode here, and I look back at my pipe element, we actually can also use FE mesh refinements for larger FE mesh lengths as well. It doesn't necessarily have to refine it into something smaller. So for this pipe element, I'd actually like to set the target FE length to something like 1.6. So this way I'm decreasing my number of mesh elements, which might decrease my solution time as well without compromising my results. So if we go to calculate, generate FE mesh, the program will automatically generate this FE mesh again, but taking into consideration these FE mesh refinements. Now, it will take just a split second longer because remember, we have really defined some of these smaller FE mesh elements for our bolts, but everything will still tie back into this 1-inch setting. So here we are with the final FE mesh. We can scroll into these bolts and see there's definitely a smaller length defined. Our pipe has slightly larger length defined. So now we are finally ready to run our first load case, and we're actually going to run the load case in the upward direction here. So the program gives me a quick warning saying, hey, you have a lot of FE mesh elements. Do you want to change the solver to iterative? I'm actually going to select no with that. This isn't a huge model, so we can keep the default solver as it is. Now, for this particular load case, everything is linear. Even the load case itself is a linear analysis first order, so it should solve rather quick here and will eventually be presented with our results graphically within RFEM. Also, no material nonlinearity shown yet. We'll get into all of those in just a minute. So now the calculation is finished, and we will be presented with our results here in our project navigator. And we're currently viewing the global deformations. And exactly as we would expect, we have our deformation shown here in the upward direction. And sure enough, our braces are deflecting in the vertical direction. But this isn't actually the focus of why I created these upward loads. I'd rather like to take a look at these elements here, my solids of the plate bearing against the pipe element, as well as the steel rod kind of encompassing the pipe. So I'm going to create a visibility by the selected objects, and I'm going to right click here to turn off the hidden objects in the background. And what I'd like to do is to still view the global deformation. So I'm going to really increase my deformation factor here. So obviously we have tension on this plate. And because everything is fully connected here, you'll see this pipe element deformation following along with that plate. Everything is fully fixed. But in reality, we know that this plate is not going to be welded to this pipe. It's actually just sitting there. So in the event of tension, we'd actually like the full force transmission here to be released. We want this to be a failure between these two elements. But in turn, if we look at the top of the element here where we have compression, we certainly want these two elements to bear on one another. We'd like the deflection to kind of follow along with the pipe along with the steel plate. So the question is, how do we define such a nonlinearity such as this? And the answer is with what's called a surface release. So what I'm going to do is to turn off my results, and under the project navigator, we'll find a new surface release here where we can right click to create a new surface release. And the surface we're actually going to generate this nonlinearity is that commonly shared curved surface that, again, these two elements share. So that would be surface number 15 here shown in the background. And we need to create a new surface release type. So I'll create a new type here. And we're actually going to release the translation in the local z direction of this surface. So it's normal to the face of the surface. So what's happening with a surface release is underneath the hood, the program's actually going to generate a duplicate identical surface. And whatever settings we set here, well, the program will either release the relationship between these surfaces or we'll have full force transmission. Now in our case, in the event of tension, we want it to fail, but in the event of compression, we certainly want these two surfaces to bear on one another. So we can set this to fixed if positive PZ. I click OK, And we want to release solid number 2. And I can even graphically select this solid here within my model. This is my pipe solid number 2. I can click OK. The program asks me to clear my results. And now we have this surface release symbol shown here graphically within the model. Now the exact same thing needs to be done at the bottom as well. Otherwise we have a fully fixed connection. So I can right click on a surface release to create a new surface release. I graphically select this surface down here, which is surface number 32. I don't need to redefine the type. We have already defined it previously, so we can simply select it from the drop-down box, and I can just type in number 2 here to release my solid from that surface, and I click OK. So now that additional surface release symbol is shown at the bottom as well. Now, what else is interesting is to take a look at this line element. And if we turn this back to a rendered view, this circular solid rod encompassing this plate, well, we also know this isn't necessarily a fully fixed connection, but rather maybe we wanted to define some type of friction behavior between the pipe element as well as the rod. So what I'll do here is to create a visibility by the selected objects, and let me show my hidden objects in the background so we can kind of see where we're at here. Well, this line element is shared between this solid rod as well as this surface, the null surface. I'm going to right click to turn on the local axis system of this line. So just like a surface release, we also have the option to add in a new line release from our project navigator. Same exact concept here. We're going to select the line graphically, line number 3. We need to create a new line release type. So within the program, it will create a duplicate identical line, and we just need to define the nonlinear behavior here. Well, for this particular option, I'm actually going to release all of my degrees of freedom. And notice we have an additional degree of freedom for rotation about the line here. And under my nonlinearities for the local z direction of the line, we can see this is in the vertical direction here. I'm actually going to set the nonlinearity to friction according to the Vy. And what this means is that it will take into account the shear force in the y direction, which is essentially the normal force pushing this rod into the pipe. So with this relationship here, we can set a spring constant. We'll set this to pretty high, 10e to the 6. We also can define a friction coefficient between the two elements at 0.8. So now the higher the shear force is, or that normal force acting on this line, then the stronger the connection between these two solid elements. Now we decrease that shear force, that normal force, then we're going to see less of a connection, and maybe we'll see that rod kind of slip around that pipe. So now that we have defined the line release type, we want to release solid number 2. And I click OK. So now we have this line release symbol shown graphically, just like with the surface releases. So canceling this visibility mode, we would now like to rerun this same model in the upward direction, but now accounting for these nonlinearities. So for the sake of time, I have actually run all 3 load cases here, and I have the results so that we can view the deformation. So what I'll begin with is obviously the overall deformation of the structure with this upward load applied here. Again, exactly as we would expect. These braces are kind of deflecting in this vertical direction. But again, probably what we're a little bit more interested in is all of this behavior that we have just redefined over on the right-hand side. So what I will do here is to select these elements, and I will create a visibility by the selected objects. Under the Display tab, I'm going to turn off my FE mesh. I'm also going to completely turn off the underlying model, so I'm only viewing the deflected shape. So with the upward direction, I'm going to increase my deformation. And now you can see that as this plate pulls away from the pipe, we actually have a gap here in between those two elements. And that's because that relationship has failed in tension for that commonly shared surface. But up here at the top, we see that the plate is bearing into the pipe element and they're both deflecting together because we have compression. So that's exactly what we'd like to see. You'll also notice too, my rod is slipping down ever so slightly due to that friction behavior that we have defined for that line release. Now, my factor is pretty large here. The rod is actually slipping down 0.01 inches, so it's nothing to be really too concerned about. If we take a look at the down position, so let's take a look at here. Remember, this load is acting down on the braces, and I can quickly cancel my visibility mode, and we can see the downward load here. Of course, our brace is deflecting in the downward direction. So again, let's take a look at the deformation factor. And you can see this plate pulling away from this pipe here with a small gap in between it. We also will see this rod kind of slipping up here as well. So this is exactly the behavior that we'd like to see defined. And of course, we can take a look at our tension case here. And if I cancel the visibility, and actually let me turn back on my model. If you remember, we just have this load being applied right along the same orientation as the members. So taking a look here at the results and the deformation, I'd like to just show you guys once again what's kind of happening with our relationship here with these elements. And you can see that when we turn this into a wireframe view and we increase our deformation here, once again, we have this element, the plate element, kind of pulling away from this pipe. So everything has been correctly defined with these deformations exactly as we would expect. So definitely the behavior that we'd like to see. Okay, so moving on, of course, the deformation is important just to make sure that the modeling is acting as exactly as we would expect. But we're also interested in information on this model, such as stresses. So for this, I can activate some of my stresses here, such as the normal stresses on my model, and both the X and Y directions as well as the Z directions, because remember, these are three-dimensional elements now. We can view the shear forces according to these color panels here. We're probably most interested in the von Mises stresses. So we can activate those here and we can take a view at maybe one of these other load cases just to view where maybe the hot spots are in this downward load case. Well, we sure have some high stresses here. Now, a quick tip when we're looking at stresses on a much smaller scale here for something like a connection. You can see the equivalent von Mises stresses are shown at 42 KSI. Under the Display tab, what I'd like to do is to activate the FE mesh and take note that under the results here, we have the solids tree. And the default here is to show the colored contours continuous within the solid. So what this means is the program is going to create a nice smoothing algorithm to tie all the values of our FE mesh points together so that we get a nice pretty picture of these various contours. The better option when we're viewing stresses on such a small scale is constant on elements. So now you'll notice that every FE mesh element has a specific color. It's no longer trying to tie those all together between each FE mesh element within a single solid. My solid stress is actually jumped up to 50.19 KSI. So this is the more accurate way to view these stresses rather than using that smoothing algorithm. Well, with von Mises stresses this high, I think this would immediately flag us that, okay, we probably need to run some type of plastic analysis. Remember, the material for these two plates is A36, so our yield strength is only 36 KSI, yet we have stresses clear up to almost 50.2 KSI. So what we'd like to do now is to take advantage of one of those nonlinear material models that we discussed back in the PowerPoint. Under the Data tab, we can see all of our materials listed within this tree. And the first would be the steel A36 from that initial solid that we defined at the beginning of the presentation. Well, if I double click on this material, you can see the material model by default is set to a linear elastic. And this is where we're actually going to change this to an isotropic plastic 3D. And these various material models for the nonlinear options, again, are available with RFMat and L. It just simply releases these material models into this main program, RFEM. So now you can see that the yield strength by default is set to 36 KSI from our A36 material based on the von Mises strain hypothesis. So we click OK through these dialog boxes. The program tells me it needs to clear out the results. That's okay. Now we probably also need to change the material for our additional plate here. These were both experiencing very high stresses. So I'm going to double click on this material, again steel A36, but we're going to modify this to the plastic 3D option available here. Yield strength set to 36 KSI, exactly as we would expect. I click OK. Now, realistically, we could change the rest of these materials to a nonlinear material model as well, but the high stresses are really in these two elements. So I'd expect to see better load distribution even with just changing these two elements alone. So now we'd like to rerun our calculation. And now that we're introducing another nonlinearity, the program takes just a minute to run that calculation. So we will just jump over to an already saved model with the results for us. So when we run this model according to the nonlinear material, and we also have these nonlinearities defined with the line and surface releases, I want to take a look at my equivalent stresses here again for von Mises. And I scroll into these particular areas that I was most concerned about, and I now look at my max solid stress of 34.77 KSI. So this is exactly what we would expect. We would never want to see with a nonlinear material model anything higher than the yield stress, because what will happen is the load is introduced to these finite element mesh points. If any of them are experiencing stresses higher than the yield strength, well then the program reduces the modulus of elasticity, it distributes the load to the adjacent FE mesh elements, and the calculation is rerun. And it's continued until the load has been fully distributed within the model. So what we're finding here are a few of these elements have probably yielded. And in order to tell if the elements have fully yielded, well, we can jump to this criteria section here. And turning this back to a wireframe view, the criteria will show us which FE mesh elements have fully yielded or have come very, very close to it. So, with these solid elements, you'll notice it's a little bit difficult to tell kind of what's going on in the interior of these solids. That's because they're three-dimensional, unlike our surfaces or our members. So what I'd suggest when you're kind of looking at these results here is to take advantage of what's called a clipping plane. So under Insert, we can activate this clipping plane, and it's exactly as it sounds. What it will do is to make a slice right through the center of our model here. So we're actually viewing the results right through the center of this plate element, and this just gives us a better idea of which elements may be a concern through the depth of this solid. We can set our step here to something like 0.2 inches, then we can use our scroll offset options to kind of scroll through the various views here of these solid elements. So I can scroll back to kind of travel through the depths of this plate element. Now we also have the ability to change the plane here. So I can change this to the YZ. So now you'll notice I kind of slice through the center of this model. I can utilize this scroll wheel here to travel into the depth of where these two solids are connecting essentially. So this will give us a better idea here using this criteria, the nonlinearity option, of essentially which elements have fully yielded. So as we kind of get closer here to our initial plate that we define, we'll see some of those yielded elements. Now we also have the ability to just quickly invert the clipping plane as well. So when I choose this option, I'm now looking at the other side of the model. We can kind of travel through there with these offset options. So that clipping plane can be extremely beneficial when you're utilizing these 3D solids, and it can just be a little bit more difficult to see. Okay, so we have really covered quite a bit in terms of these material solids, nonlinearities. The next thing that I would like to show you guys is how to activate a null solid. And we might think of using a null solid for this particular connection if all of a sudden we're told that, okay, this diagonal brace here isn't going to be a double channel section, but rather it's just going to be a single channel. So we'd actually like to get rid completely of one of these channel elements. Well, of course, we can go in here and delete the geometry, but instead, I'm going to double click on my right solid here, and I'm going to change the solid type to null. And I click OK, so we clear our results here. And you'll notice that the program automatically modifies the color here to this red. Well, that just means that this channel was completely taken out of the model, and all associated loads will also be taken out of the model for our next calculation. So before we run that calculation, remember we need to kind of modify what's going on at the front here because we created all those rigid surfaces to distribute the load evenly. So I create a visibility by the selected objects. And what I'd like to do is all of my rigid surfaces here on the right weren't automatically changed to null surfaces either. So what we can do is just to go ahead and select them all with our selection tool. We can right click to edit the surface. And similarly to the solid, we simply change these rigid surfaces to null. And I click OK. So now all of these surfaces and this solid on the right has been completely deactivated. The final thing to do is just to modify where we're applying this load. Currently it's applied to this node that's really no longer active on that surface. So let's take this load and just simply drag and drop it. And actually, let me zoom in here a little bit closer. We'll take this load and we'll drag and drop it onto this node on the left. So now that will be evenly distributed to the face of this channel section shown on the left. Same thing for the downward load. I'm going to zoom in. I can just grab this load here and I can drag and drop it and snap it to this new node point. And finally, we have this tension load, same concept. I would just drag and drop it to this new node over on the left. So now we're ready to run our analysis again. Maybe we want to change the materials back to linear. Maybe we keep them as nonlinear, whatever you prefer. So we rerun that calculation. And once again, I will jump to an already saved model. And let's take a look at this upward load case. Let's turn on our results. We're currently viewing the global deformations here. Let me turn these on. I will turn off the model in the background completely. And now you can see that although that channel section exists still on the right-hand side, we've set it to null. It's completely taken out of the calculation. We can rerun this entire connection with only a single channel shown. But in the event we need to reactivate that solid again, all we need to do is just to change the material model back to a material, the material solid back to a material element instead of null, and then maybe modify these loads slightly, and then you can rerun it with the double section shown. So that's a great example of how we can use that null solid option. All right, so that obviously makes up a bulk majority of our example today. I want to touch on a couple of the other solid types before the end of the presentation today. So we'll jump to another model here, and this will actually be an example of a solid gas element. And you can see here that this is an inflated foil cushion. And these might typically be used on roof elements, for example. And this element is actually quite large. It's 40 feet in length and 13 feet in width. And the elements that have already been defined here, and I'll also preface this with one of my colleagues did a webinar completely devoted to this foil cushion and utilizing our form finding add-on module. So you can refer to our YouTube channel to view a webinar that goes much more into depth than what I have time to show you today. But point being, we have a surface element at the top here, and our stiffness cannot be set to a null stiffness when we're defining a gas solid. The gas must be encompassed by some type of element here. So for this, we have a fabric membrane defined with a membrane orthotropic. And we're also utilizing our form finding module, which this is used for tensile fabric structures. We can apply a pre-stress force. And the program will essentially utilize this add-on module to find the relevant shape based on these pre-stress forces. So that is the surface that's defined on the top. Exact same concept for the surface defined on the bottom, another membrane orthotropic surface defined. Now, what's interesting is that if we take a look at here, we have our solid already defined, and this time the solid type is set to gas. You can see the material comes from our material database, which instead of filtering to steel, for example, we filter to gas. And we have all of the relevant gas along with their gas properties shown within this table that you can select from, or you can always create your own as well. So in this case, we're using dry air. The second tab is where we will set the initial atmospheric pressure of 14.5 psi. The initial temperature is set at 74 degrees Fahrenheit. So that really makes up the solid definition here. And before we run this first load case to find the fabric form finding shape, I also want to point out that a solid load has been applied to this model as well. And we can add in a new solid load from this drop down. And I can double click on it graphically here, and you'll see that a solid load can be defined with the load type gas with a resulting overpressure, and then we apply the magnitude of 6.25 psf to the interior of these fabric membranes. So when we run our analysis, what we'll consider is the form finding shape from the pre-stresses. We're also considering the solid gas and the solid gas load altogether. So when we run our analysis, maybe initially we can view the contour lines of the shape just to see the nice contours that we would see with this inflated foil cushion. But we're probably also interested in information such as our solid pressure. We can view the overpressure, for example. Gas volume is given to us here, and as well as the temperature, but the temperature is just going to be that 74 degrees that we initially set it as. So with these foil cushions, this initial load case is interesting, but we probably also know that it's going to be presented with some additional loading scenarios, such as snow load on a roof. So what we can do in this second load case is to also add in a 10 psf snow load to it. So when we rerun this calculation, we'll now consider this area load on top of these fabric membranes. We've also applied an additional solid load in the interior here, a little bit higher than what we saw with that initial load case. So now when we look at our results here for the global deformations, we're seeing the downward deflection of our entire system. So what's important to note here is that without this gas solid defined, if we were to apply an area load, well, this would just be applied to the fabric membrane on top, and it'd probably pass right through the bottom fabric membrane. But as we have it defined now, well, we have this interior solid with gas properties. So both of these elements are actually deflecting together. So quite powerful, again, in how we can use a gas type solid. So the final example for today is going to be a contact solid. And for the sake of time, as you guys can see that we're almost out of time, so I don't have the ability to model this one from scratch. I do have a previous webinar that I do a very similar beam splice application such as this where I model it from scratch. So just shoot us an email after the presentation. I can point you to that. But really, I just want to give a quick overview of this contact solid. So again, this is a beam splice. And over on the left-hand side, we have an HSS 16 by 8 with 0.5 inch thick walls defined. Now these are all defined with surface elements. So you can see the relative material defined here, the relevant wall thickness for these surfaces. Now it's also attached to a steel plate here. And this steel plate is a standard stiffness with steel A36 defined, and my thickness is set at 0.25 inches. Well, over on the right-hand side, we actually have the exact same setup for an HSS member. It has its own steel plate defined here as well, 0.25 inches thick. So in between these two steel plates is where we would define our contact solid. So let me go to a wireframe view here, and I can double click on my solid that's kind of existing between these two surface elements. You can see the solid type is set to contact. So before moving on, let me quickly jump to the PowerPoint here just to explain a few important points about contact solids. So the contact surfaces must be parallel and identical. And what this means is that any nodes or lines that exist on surface A, and in our case, that's the steel plate on the left, they must also exist on the right-hand side. Everything must be identical. Surface boundaries must be defined with 4 lines. So that means exactly 4 lines. It can't be defined with 3. It can't be defined with 5. If we have complex curved contact solids, well, what we'd want to do is to break this down into multiple simple solids instead and apply all these same rules. We want to adjust the surface FE mesh to accommodate the single FE columns between contact surfaces. And what I mean by this is we have in this picture up here on the right, we have surface A on the left, we have surface B on the right. Well, we'd want to adjust our FE mesh so that it's giving us accurate results. It's small enough in that there's one single FE mesh element that's going to be drawn from surface A to surface B connecting. And that kind of circles back around of why these two surfaces must be identical. And finally, we have the ability to define the perpendicular and parallel force transmission, different definitions available in these drop-down boxes. There's actually quite a few options. So I took a quick snapshot here from our help file. This table shows all the different options, gives a nice picture and a relevant description. So definitely refer to the RFEM help file if you're interested in learning more about what options there are for the contact solid. So going back to our example here, we can see under the second tab, the contact is between surface A, which I said is surface number 9. The program automatically detects surface B as 18. For this beam splice, I want the behavior between these two parallel steel surfaces to fail under tension. And as far as the contact parallel to surfaces, you can see here we have many different options, including rigid friction, elastic friction. I'm going to set this to failure if the contact perpendicular to the surface fails. So this is for my shear behavior. It'll simply fail if we have failure under tension as well. So once this contact solid is defined, a couple other things to note. The exact depth of this contact solid is really important. So I can use my measure tool here and I can measure the depth of this solid between the two surfaces, and it's 0.25 inches. The exact depth should be 1/2 the thickness of surface A plus 1/2 the thickness of surface B. So in my case, both surfaces of these plates were 0.25 inches. Therefore, my contact solid should be 0.25 inches. So that's really important in order to replicate these surfaces essentially lying flat against each other. Now, the other final thing to note is that, of course, these plates are going to fail in tension, so we need something to hold them together. Well, I have modeled some just typical member elements here as beams, and these are just circular steel sections with a 1-inch diameter to represent my bolts. So these bolts should take over on tension when the plate elements fail. So we can apply our first load case here, which you can just see is some simple line elements kind of along the walls of this HSS member. So when we view the deformation, what we should see if we take a look at this is some strange behavior at the bottom. And what will help clarify kind of what's going on here is under the display tab, we can activate here this option here to remove contact solids from display. So when we're looking at the deformation, it's quite apparent here where our plates are failing in tension, and those bolt elements are kind of holding those two elements together. But up here at the top where we have compression, we can see those plates kind of acting together because they are working with full force transmission. So under the results tab, what else we can view is to expand out the members option, and we can actually view the tension forces as the normal axial load in these small bolt elements. And as we'd expect, we have a higher tension load for those bolts at the bottom. And as we kind of move up the plate, a much smaller tension load, if any. And finally, we're probably also interested in the results on our surfaces. So we could take one of these steel plates, for example, and create a visibility by the selected objects. We could view the von Mises stresses just to make sure we're not exceeding any of the yield stresses here. And we have the magnitude shown at 13.2 KSI. So I'd say that's pretty good for this connection. We also can turn the model around here to view the additional plate on the other side as well by selecting the visibility by selected objects. Slightly higher stress here at 15.44, but still relatively okay. So all of these models today will be available on our website. Under support and learning, you can go to webinars, and the relevant webinars will have all of these models to download. So you can take a look at these and play around with them, even in the trial version of RFEM. So that will conclude our webinar today. You can always visit our website at dlubal.com to learn more information about RFEM, any of these add-on modules. You can view previously recorded webinars such as this one. Also take a look at some of the knowledge-based articles, technical articles, and FAQs, not only on our software, but just general engineering topics. As well, on our website, feel free to register for one of our upcoming online trainings, or you can even download a free 90-day trial version of RFEM, again, to take a look at these models that we went over today. If you have any questions about today's presentation or anything else, feel free to contact us in our Philadelphia office, and you can see the contact information at the bottom of this slide. The phone number is 267-702-2815. Our email is info-us@dlubal.com. So we will have many more upcoming webinars. I try and do them about once a month. You can register on our website at dlubal.com under support and learning and webinars. As most of you know, I send out a reminder email about a week before this will take place, so feel free to register directly through there as well. Many of you are wanting PDH certificates. That's great. These will actually automatically be emailed to all participants today who were available for the full presentation. So that is a requirement from the states that we are pre-approved providers, that if you want a PDH, you must be here for the full presentation. So again, these will automatically go out approximately within a day or so, so maybe not immediately. Now, if you yourself did not register with your own email and your own name, perhaps you're watching with a colleague, you would need to request a PDH at info-us@dlubal.com. So again, if you yourself did not register with your own name and email and you're watching with a colleague, please send us a PDH request at info-us@dlubal.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next presentation. Thank you.